All right, question 2 says to compute each integral below, and part A, we're looking at the integral of the function yz e to the negative x over the solid box as x runs from 0 to 2, y from -1 to 2, and z from 0 to 3. Okay, so we know from the Fubini theorem that we could set this up as an iterated integral in any order we like. And since the x integral would be the most complicated, it's this exponential, I'm going to do that one last. Okay, not that it matters. I mean, the Fubini theorem says the result will be the same no matter what order you choose, but I just don't want the e to the various powers to be cluttering up the integrand as we move forward. So I'll go ahead and put the x bounds on the outside, then I'll put the y bounds and then the z bounds. Okay, so we're doing a dz dy dx integral. And so for the z integral, that's going to give us y times z squared over 2 times e to the minus x. And we're evaluating as z runs from 0 to 3. And then we have our dy dx. So now go ahead and evaluate at z equals 3, and that's going to give you a 9 over 2. So we'll put that here. And then if I plug in 0 for z, I'm just going to get 0. So there we have it. All right, so I'll go ahead and pull that 9 over 2 out in front in the next step. So that's going to give us 9 over 2, and then we're looking at integrating y e to the negative x with respect to y. So that's going to give us y squared over 2. And then we have our e to the negative x, and we're evaluating from -1 to 2 for y, and then we have our dx. Okay, so then go ahead and evaluate there. Plugging 2 in for y is going to give us 2 squared is 4 over 2 is 2, so 2 e to the negative x. And then plugging in -1 is going to give us half e to the negative x. And so now 2e to the negative x minus a half e to the negative x, that's going to be 3 halves. Oops, sorry about that. Now, it's still the 9 halves out front, right? I'm saying 3 halves e to the negative x inside. And now go ahead and pull the 3 halves out front, so it'll multiply the 9 over 2. And so we're going to get a 27 fourths out there. And then we're going to integrate e to the negative x with respect to x. That's going to give us a minus e to the minus x. And now evaluate from 0 to 2. And so that's going to give us 27 fourths times the quantity, well, minus e to the minus second power. And then plugging 0 in, we're going to get a minus e to the 0, so a -1. So I'm subtracting a -1. So if you put that all together, I'll write this in a slightly cleaner form. It's going to be 1 minus e to the minus second power. Okay, so there is our answer. And I do want to make a note here on an alternative way to compute this that would be quite a bit simpler than this. Notice, like we saw in for double integrals, okay, if your integrand is of the form where you have something that depends only on x, so here's be the e to the negative x, something that depends only on y, that's just the y, times something that only depends on z, right? We can break up this iterated integral as a product of single variable integrals and then just compute those. And you can see, right, how that's happening in all of these steps, right? The 9 halves came out. Well, the 9 halves is just the integral of z from 0 to 3. And then the 3 halves came out and multiplied the 9 over 2. Oh, well, the 3 halves is just the integral of y. And then lastly, we integrated the e to the negative x, and that gave us the 1 minus e to the minus second. So this is another way to do this, and while this is perfectly fine, you can see it's just a little more cumbersome, more room for small errors. So do keep this in mind when it's available. I recommend taking advantage of it. All right, so now let's look at part B. Okay, notice I can't split this integrand up in that special form because all the variables are inside the cosine, but nonetheless we can still compute the integrals just fine. Notice here that we do have some variable bounds of integration, and in the next couple problems on the worksheet we will look at what those bounds are telling us in relation to the regions in space that we're integrating over. But for the moment, right now in this problem, we're just going to focus on the calculation. So let's get to calculating. To do the z integral, well, we're integrating cosine, so we're going to get a sine. And then from that 2, I'm going to go ahead and divide by 2 from the chain rule. So I'll get 1/2 sine of x minus y plus 2z, and z ranges from 0 to x. And then we have our dx dy. So now plug in x for z, and again this can get a little bit confusing. If you want to write in those bounds, you know, z equals 0, z equals x, that's not a bad idea for these problems. I'll also go ahead and pull out this half just to simplify the integrand a little bit, so that half can come out front. So what are we going to get? We're going to get the sine of, and this is going to be x minus y plus 2x. So x and 2x would give us 3x, and then we're subtracting the y. So I'll make a little note here that the 3x minus y really came from x minus y plus 2x. And then we just combine those x's. Alright, and so now if I plug 0 in for z, what is that going to give us? That's a little simpler. It's just going to give us x minus y. Alright, and then we have our dx dy. So keep going, right? We have our 1/2 integral from 0 to pi over 2. And now we're going to integrate with respect to x. Okay, and so here I'm going to get, well, it's the integral of sines. This can be minus cosine. And then I'm going to have to divide by 3 from the chain rule. So it'll be minus 1/3 cosine of 3x minus y. And then here I'm integrating minus sine of x minus y with respect to x. So that would be a plus cos of x minus y. Notice the chain rule factor that it would be 1 because of the 1 in front of the x. So we're good there. And then we're going to evaluate all of that as we let x range from 0 to y. And then we have our dy. Okay, so let's go ahead and compute this. Plug y in for x. So that's going to give us a minus 1/3 cosine of what? Well, 3y minus y, that'd be 2y. Okay, then we're going to get plus the cosine of y minus y, which would be the cosine of 0, which would be 1. And let's make a little note there where that's really the cosine of y minus y, which is the cos of 0. And that's equal to 1. And as I said this out loud, but I'll make that note too. This is really the cosine of, what was it? It was 3y minus y, which is where we're getting that 2y. Cool. Okay, so that's what we get when we evaluate at x equals y. So now what we're going to have to do is subtract from that what we get when we plug in 0 in for x. So we're going to get minus 1/3 cos of, so 0 is going in for x, that's going to give us a minus y. And then here, plugging 0 in for x is going to give us a plus cos of minus y. Okay, and so now let's compute all that, right? You can see this is getting kind of cumbersome, but each of these individual integrals, fortunately, is not too bad. Now, there is something I can do here in this parenthesis to simplify, so let's go ahead and do that. This right here would be, well, minus 1/3, and the cos of minus y is just really the cos of y, because cosine is an even function. So this is really minus 1/3 cos of y, and then I'm going to have plus the cos of y, again, because cosine is an even function, and so then that simplifies to 2/3 times the cos of y. Okay, so that's nice, a little bit of a simplification. So plugging away, now we have 1/2, and so we're going to integrate with respect to y, and so we're going to have minus 1/3 times what? Well, we're going to integrate the cos of 2y, and so that's going to be the sine of 2y, and then we have to divide by 2 from the chain rule. So that's going to be 1/2 sine of 2y. So we're going to get it minus the 6th out front there. Then we get plus y. And then here I'm subtracting the integral of 2/3 cos y. So I'm going to just get minus 2/3 sine y. All right. And then we're going to evaluate that from 0 to pi over 2. So we're getting there. So let's see. When I plug in pi over 2 in for y, I'm going to get the sine of twice pi over 2. That's going to be the sine of pi. Ooh, that's 0. That's awesome. And notice when I plug 0 in for y, this is also going to be 0. So this thing actually is really just going to contribute a 0. That's great. How about the y? I'm going to get a pi over 2 there and a 0 there. So I'm going to get a pi over 2 from the y term. And then here I'm going to get minus 2/3 times the sine of pi over 2. And the sine of pi over 2 is 1. So I'll get minus 2/3. And then when I plug 0 in, sine of 0 is 0. So I am done. Okay, I'll go ahead and rewrite this a little bit. If we get, say, a common denominator there of 6, then I can, I'll have a 6 down here, and I'll multiply that with a 2 to get a 12. And then I'll have a 3 pi minus 4 upstairs. And so there's our value. A little more heavy, but fortunately, you know, just each of the individual integrals were not hard. It's just, again, you know, room for small errors. But there you go. All right, great. Thanks.